A solid insulating cylinder of length L equals 9 meters and radius R equals 3 centimeters has a total charge of 2 microcoulombs spread uniformly throughout its volume. That means a rho, a volumetric charge density. What is the magnitude of the potential difference between a point along the axis of the cylinder and a point on its outer surface, radius R? Okay, so I'm going to draw a quick picture because that's the way you start every physics problem. You have a cylinder and you have a center and you want to find the potential difference, i.e. voltage, along this radius, big R. And yes, the way we're going to do this is we're going to start by finding the electric field. And we're going to find the electric field using Gauss's law. And so this would be an A. That's going to give us our electric field. Then once we have the electric field, we're going to use that to find potential. The definition of E equals negative E dot dA. And so we're going to find the electric field at any given point along 0 to big R, and then we're going to plug that in to our definition of voltage. Okay, so let's start by writing out Gauss's law. So the idea with Gauss's law is it's Q enclosed, the enclosed charge over epsilon naught equals integral E dot dA. And there's some nuance here that you really should appreciate. So for starters, E is the electric field, and since this is circularly symmetrical, it's the radius, the electric field is going to go out radially, so it's going to go out radial direction. dA is the area vector, which is written perpendicular to the surface. So this will be dA here. And so these are both vectors. A dot product creates a scalar based on how parallel two vectors are. So they're both radial, and so they're both going to be pointing in the same direction everywhere. And so this dot product is just going to be E times dA. And more specifically, the electric field is going to be uniform for a given radius, since it's radially symmetrical. And so since it's uniform or constant, we can pull it outside the integral, which gives us E integral dA, which the integral just dA is the area. And this is going to be the area of our Gaussian surface. And our Gaussian surface is going to be a cylinder that's inside our larger cylinder, concentric to, and it's going to be of a variable radius. We're going to call this small r. So we're going to do small, we're going to find the electric field for any given radius on the inside, going from 0 to big R. And then we're going to use that for our voltage. So this kind of gets the right side of our equation. Now let's look at the left side of our equation over here. We're going to look at Q enclosed. So Q enclosed is going to be related to rho, where rho in this case is the volumetric charge density, which is defined as a small bit of charge for a small bit of volume. But since it's uniform, we can use Q total and volume total. So Q total, that's just given. Volume total is going to be the volume total of our shape, which is going to be the area of the face, pi r squared, big R squared, times length. And so Q enclosed is going to be, let's see here. Yes, so Q enclosed, I'm going to call this, and this is going to be equals Q enclosed over volume enclosed. It's all the same thing, delta Q or delta volume. Q enclosed is going to be the enclosed volume of our Gaussian shape as it's getting bigger. And so that is going to be pi small r squared times length. So it's going to be kind of the concentric smaller cylinder. Nope, that's going to be the volume enclosed. Oh, fail, tragic. That's okay, we got this. Nope, except for that C, that one almost escaped. So that's going to be our volume enclosed. And then Q enclosed is what we're looking for. So we're going to solve for that. So rearranging this portion, I'm going to say that Q enclosed equals volume enclosed over volume total times Q total, which is going to be volume enclosed, which is pi small r squared times L over pi big R squared, also times L, times Q total, which is just a given. Simplifying this, cancel, 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 cancel. We get R squared over big R squared times Q total. All right. So now we have everything except for the area of our Gaussian surface, which I didn't talk about yet. I'm going to do this in yellow just to create some sort of link between these two concepts here. The area of our Gaussian surface is just going to be the circumference of the circle, which is 2 pi r. It's going to be small r times length. And you have r, which has dimensions of meters, length, and L, which stands for length, which also has a dimension of length. Therefore, we have area is meter squared. Seems plausible. All right, write everything out. Q enclosed, which we know is R squared, big R squared, Q total, divided by epsilon naught. Do this Q total over epsilon naught equals, and then we're going to say E, which is what we're looking for, question mark, times 2 pi r L. Feels like I'm missing something. Maybe not. We'll see. We'll see how this works out. So solving for L, or solving for E, we get E equals R squared. Oh, let's cancel one of these. So we have just a single R. So we have R over 2 pi epsilon naught R squared L. Let's see, E, oh, and Q total up top. So we have Q total, a single R, epsilon naught. Yes, and then I'm going to multiply this by 2 over 2. That gives us 2 times 2, which is 4. We have 4 pi epsilon naught, and 4 pi epsilon naught is the same as K. So we have K 2 R Q total over big R squared times length. Maybe, quite possible. All right, so this gives us a, and then we can do a little R direction here and make this a vector. This gives us a formula for the electric field at any given point along here. You might be thinking, well, electric field, I'm used to something like E equals K Q over R squared, or E equals K, maybe it's like 2K lambda over R for a linear charge. Yes. The reason this has an R up top is because as the cylinder is getting bigger, it's also picking up more charge. And so it's kind of a balance between picking up more charge and moving away from the central axis. So as it moves away from the central axis, the electric field is lowering, but it's also picking up more charge. And so that's kind of having two competing effects. All right, so now for the voltage part. Voltage equals negative integral E dot D. I do say dx, but that's just really displacement. In this case, our displacement is out radially. So instead of x, I'm going to use dr. And dot product together. Now I'm going to say, plug in the values, negative integral 2k r q total r squared L dr, everything here, and we're going to go from 0 to big R. 0 to big R. So now we're going to plug these values in. I'm going to pull out the constants. So we're going to have negative 2k small, no, 2k q total. So Q total over r squared L times integral r to 0 I'll go with the negative r dr. Maybe, we'll see. So then this becomes r squared over 2k, I'll leave the negative in. I know, it doesn't matter. 2k q total r squared over 2 r squared L. The r becomes r squared over 2, but we're evaluating it from 0 to r. So the 0 goes away, the r squared just becomes big R squared. Cancel, 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 cancel. We're left with negative k q total over L. So putting some numbers to this, I get k, which is 9 times 10 to the 9th. Some people use 8.99. I'm going to use 9. Q total, which is 2 microcoulombs. So I'm going to call it 2 times 10 to the negative 6 coulombs, all over a length, which we were told is 9 meters. Cancel, 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 cancel. 10 to the 9th and 10 to the negative 6 becomes 10 to the 3rd. We're left with 2. 2 times 10 to the 3rd is 2,000. And since we're talking about potential, this is going to be 2,000 volts, negative 2,000 volts. So we come up here. All of our answers are positive. They asked specifically for magnitude. So I do think the difference between the center and the top is probably negative 2,000. So yes, so it's probably 0 volts, some positive number of volts, and some positive number of volts plus 2,000. So it goes from 2,000 to a constant plus 2,000 to a constant on the outside, and so there's a 2,000 volt difference. The answer probably is negative. It's just they're asking for the magnitude, so we're going to give them the magnitude, which is C, 2,000 volts. So, hope that helped. See you next time.